Do opposites exist, and how can they inform multimodal learning? This may seem like a simple question, one presumably encountered first in kindergarten. What does it mean for two things to be opposite each other? Does not the question speak for itself? There are so many examples of autonomous phenomena in everyday life when you stop to think. We have light versus dark, up versus down, happy versus sad. Could it not be any clearer? This inquiry may seem apparent and hardly worth exploring, but this is where the mind can prematurely lock itself down, assuming it knows more than it does. After all, as nearly all optical illusions demonstrate, our perceptions are often limited and even times distorted. Consider dimensional illusions like the Ames room effect, where an object's size vis-a-vis its distance confuse us as to its true nature. Or consider the color and shape contextual illusions, where an image shade appears to completely change based on surroundings. Why are these illusions so powerful as to bedazzle and confuse? They point to a hidden truism about life and the human receiver. In trying to make sense of what seems to our minds to be as we gaze upon an object, it evaluates the properties not in isolation, but based on prior knowledge and what surrounds it. In a sense, the sense of context shapes a broader understanding of reality, but its impact on how we see the world and communicate with others, that sense of reality is not limited to merely the visual sense. In conveying the truth as we best understand to others, a special type of figurative language is devised, one which paints a picture with the mind's eye, further formulating how we evaluate information. In utilizing such figurative language, oftentimes a spectrum or spectra is utilized to hint context cues, yet the process is rarely understood consciously. To grasp more deeply why words like up and down are employed to convey such a multitude of things, not only directions, but temperature, mood, monetary values, and the like, we must examine the workings of language to understand how and why implicit quantitative and comparative measurements are commonly used in the form of spectrum. First, let us dissect the nature of the nomenclature. There we will find that the terms we use to filter our information make the point, may out of necessity create limitations and distortions of the big picture. When using spectra as common description, we effectively assign data points on a u-dimensional continuum, for a line can only represent two directions. Therefore, when one places various data points on a continuum, be it up or down or left or right, we get a chance to compare the quantitative value of all the data given. But we must not forget the importance, significance of comparative information. Our mind at best compresses higher quantities of data into a smaller container, much like a high-resolution Adobe image is compressed to save space into JPEG. The fine details may be lost, but one would hope the pertinent points are not lost in translation. We tend to take for granted the meaning of these contrasts through language behind them, but this is where we limit ourselves, for we cannot truly comprehend the nature of the yardstick that we use to measure things until we look beyond it. Otherwise, we are like the fish that when asked how's the water answers, what's water? To examine this query more deeply, let us look at a not-so-obvious example of colors. We all have been told since we were children in art class that there are three main primary colors, red, yellow, and blue, and the remainder are secondary colors such as orange, green, and purple. Then we find that there are arguably an infinite number of combinations when one mixes different ratios, and a further intricacy adds brightness and saturation. But we've barely scratched the surface of the color knowledge. After all, pigmentation colors and light colors work differently. Therefore, when dealing with the latter, we come across a totally new dichotomy of things such as additive and subtractive colors. Therefore, an art and a science is the definition of colors and color opposites. If one were to take a color spectrum and keep in mind the human eye can only see a small fraction of what exists, and place it on a rainbow ruler with it, you get a full range of frequencies that correspond to each other. As you can see from the image, the frequencies of colors as follows. Red equals 740 to 625. Orange equals 625 to 590. Yellow equals 590 to 565. Green equals 565 to 520. Cyan to blue equals 520 to 500. Dark blue to indigo equals 500 to 435. And violet equals 435 to 380. There are further complications to this equation when you consider how there are only 3 cones in the human eye and the rest are guessed, but that's beyond the scope of this discussion. Now let us take this rainbow ruler and bend it into a circle. Suddenly the notion of color opposites becomes clear and makes sense, for we can see the colors facing each other. But wait, think about it. How can 740 to 625 red be opposite 520 to 500 cyan blue, or 590 to 565 yellow be opposite 500 to 435 dark blue to indigo, when all these are merely different points on a wavelength of continual wavelength of light? And when you include additive and subtractive colors, the equation becomes even more complex. Okay, the color spectrum quantities are maybe more than meets the eye, no pun intended. But what about chemistry? Do we not have opposites there when we have 2 chemical components that counteract each other, like acids and bases? Or could we not use the example of direction? We have longitude, latitude, and altitude. So we know if you walk 2 blocks west and retrace your steps 2 blocks east, you'll end up where you started. Pretty simple, right? Well, wait again. Since the Earth is round, we will eventually, going any direction, end up in the same place. Therefore, east, west, north, and south are relative to where you are. Even up and down do not exist once you leave Earth. Consider how it must feel like to be an astronaut in outer space without any directions we would recognize. Does all this evidence suggest the notion of opposites to be nothing more than an illusion? Perhaps, if defined in absolute terms, but that stated in at least relative terms, opposites are a phenomenon that displays components of reality and our ability to contextualize and compare bits of information. Both the literal and figurative language of this concept helps us make sense of the world. I pose that all this mind-twisting information, not to make you dizzy or disoriented, but to make a greater point. At times we must pull back the curtain of the limitations of our perception in order to see the big picture. This is why you can escape an optical illusion awestruck, the profound sense of yourself in the world. Through examining the gaps in our awareness and questioning our source of understanding, we can free ourselves from its confine. Exit Plato's cave, if you will, liberated to rebuild deeper knowledge. It is in this existential examination we can rebuild a fuller understanding of reality, one that can provide you with the tools to open your students' minds. In both the coding of this revolutionary language software and its usage and presentation, you can show in pictorial form, automated into its structure, how components of information are juxtaposed to each other. With all this in mind, let us consider how this understanding enables us to approach components of mathematics in a manner students can understand. In the old days, arithmetic was customarily taught in a linear procedural-based fashion. This was due to the fact that base 10 requires many step-by-step process to utilize, i.e. how to calculate placement value and the regrouping of numbers while solving a problem, such as carrying and addition and multiplication, borrowing and subtraction, or applying both to division. With all this left-brain processing computation, the deeper logic of mathematical operations needed for algebra onward can appear as a foreign language to students taught math the old-fashioned way. It is applying computational and accustomed to computational and linear logic to problems ultimately need to be seen in dynamic, conceptual, nonlinear thinking. This is why the Common Core has long attempted to devise a more conceptual approach to teaching arithmetic through processes like number facts and families and the like. However, these innovations have often fallen short of desired effect because the one thing teachers have often not been given enough background in the concept of mathematics seen this way, the degree of computational, procedural, and conceptual frameworks. Therefore, this new multimodal system will provide teachers with a toolbox of properties to assign these varying components in mathematical education that can bridge the computational and conceptual components. By using dimension and color coding, visualization of operations such as can be used, such things as the placing on an X and Y axis. Different colors and spatial layout can be utilized through a treasure chest type cataloging of placement value distinctions. Once again, understanding the way our mind currently classifies information, especially numeric information, and compare and classify values is key to unlocking a deeper understanding of the logic of mathematics, enabling you to impart these facts and comprehension to your students. A similar process can be applied to language and literacy. After all, reading can only come alive for students when the rules and technical applications can be joined in the process of instruction. The tragedy of our current reading wars, now bleeding into mathematics, is that we keep fighting battles over things such as semantics, the content focus of such programs like balanced literacy, versus a phonics-based approach that would seem to be discussed today. The multimodal approach enables a teacher to place in a classroom kind of modalities used in shows like The Electric Company half a century ago, where it's bridged demonstrating the meaning of words through visualized representation, simultaneously breaking down components of words, vowels, consonants, and other sounds alike through verbalization and color coding. This concept all surround conceptual understanding of learning. Our emerging knowledge of the human mind, aided by our technological advancements in AI, an understanding of language models and neural networks, gives us a novel insight into comprehension. Such processes will enable teachers to present and explain contextualized information, enabling the form, function, pattern to be displayed within all content. Synesthesia, the blending of senses, has enabled me to see the world through a unique pair of eyes. This ability has been a gift to me, much as it has been through Daniel Tammet, who has mastered 9 languages in advanced mathematics through his internal mind mapping process. Hence, this is my gift to the world, to show how learning works. We can bring today's classroom into the world of tomorrow through immersive learning. Thank you.